So in this next lecture, we are going to cover surfaces and interfaces, right? How do you go about modeling surfaces and interfaces using DFT calculations, right? And obviously, surfaces and interfaces are very important for a lot of properties. A lot of you are in nano engineering, and obviously surfaces contribute a lot to the properties of nanomaterials, right? So simply because when you go to nano-sized materials, your surface area is a much larger proportion compared, much larger fraction of your bulk atoms, okay? So we have seen this slide before. Basically, so far, most of the materials that we have been simulating are perfect infinite crystals, right? So in other words, we are not assuming that there are no defects in them, there are no surfaces, there are no interfaces. And real world materials are of course not like that. And the surfaces and interfaces can have a lot of impact on the property of the material, okay? And in fact, in some applications, the surface or the interface is the actual so-called material or application that you are working with, okay? So just a recap of the supercell method, all right? So when we try to simulate defects, the way that we create a model defect system is to take a bulk unit cell and then create a much larger supercell, and then change one of the atoms to, say, if you want to substitute dope aluminum into copper, we will substitute one of the atoms from copper to aluminum, and then that gives us a model doping structure, right? Now, when you want to model surfaces, you can essentially use roughly the same concept, right? It is a bit different compared to just a substitutional defect, but the general principle is the same. In other words, you will create a big cell, and then you modify the big cell to basically get you your model system that simulates what a surface is, okay? So this is basically how you go about creating a surface, right? Let's say you take this FCC copper crystal, and you want to simulate the 100 surface of copper, right? In other words, this surface termination, this cube surface right here. Now, what you would do is that you basically would create a supercell that is long in one single direction, okay? So you just take this cell and you replicate it in one direction until you basically get this very, very long cell. And then what you would do is that you then remove, let's say, half the atoms or some fraction of the atoms in your supercell. And once you actually remove the atoms, basically this what you have exposed right here is basically the 100 surface of your copper, okay? So if you do a calculation using this slab structure, you slab plus vacuum structure, you basically get you are essentially simulating the surface, the 100 surface of your copper copper metal, okay? So this may seem small, but remember you have periodic boundary conditions in all directions. Essentially, you are simulating an infinite surface, and you have multiple, once you actually do periodic boundary conditions, you essentially have repeated surfaces across all the third dimension, okay? Now, one thing you need to keep in mind is that whenever you create such a slab plus vacuum system, you are essentially creating two surfaces per unit cell, right? You're not creating just a single surface. You always create two surfaces with a slab plus vacuum structure, okay? So how do we define surfaces? Okay, so there is actually a very well-defined crystallographic definition for lattice planes, okay? So essentially, a lattice plane for a given Bravais lattice is a plane or a family of parallel planes whose intersections with the lattice are periodic, right? So in other words, they are described by 2D Bravais nets, and they intersect the Bravais lattice, okay? So, or equivalently, if you want to have a simpler conceptual definition, basically a lattice plane is any plane in your crystal that intersects with at least 3 non-collinear Bravais lattice points, okay? So if you look at this crystal, this is basically the 111 surface of your crystal. This is yet, and this actually looks like the 110 surface of your crystal, and basically these are all the lattice planes. Okay. Now, when we talk about lattice planes, we denote them using what are called Miller indices. These are essentially this bracket with 3 numbers. Okay. The numbers are usually H, K, L, and these numbers are integers, okay? And the way that you, the definition of the Miller indices, this is a bit beyond the scope of this this course, okay? So if you are interested in figuring out how lattice planes work, you should take a crystallographic course like NANO266, where they will go through with you how all these lattice plane, how these Miller indices are defined. Okay. Here, what you just need to keep in mind is basically that your lattice plane, your Miller indices essentially define a unique plane within your crystal structure, and when you are actually doing surface calculations, you need to define which of these surfaces you are calculating, right? So, for example, if you're calculating the 221 surface or the 112 surface or the 021 surface, all these are different lattice planes, and all these can have potentially different surface properties, okay? All right. So how do you go about constructing your surface planes? Essentially, there is an algorithm that you can use. Essentially, what you need to do is that you first orientate, take your unit cell of atoms. You then, based on the Miller indices of the plane that you're interested in, you will reorientate your unit cell in that direction. Okay, so you redefine a unit cell that has one of the surfaces, one of the unit cell planes in that surface plane that you're interested in. And then once you actually create this oriented unit cell, you can then do the supercell method to basically construct your surface plane. Okay, so the example that is shown here is basically the 10-14 surface of Fe2O3, and this is how you go about constructing this surface plane. Okay, now once you actually construct the surface planes, of course, you can actually also do a further transformation to get a more orthogonal-like surface plane. But this, depending on your system, this may or may not be necessary. Okay, so obviously this is a very abstract and generalized approach to creating surface planes, and for very complicated examples, very complicated crystal structures, this is basically the way you will go about doing it. In your lab number 4, which is something that you will do 2 weeks down the road, you will also be constructing surface planes, but in that case, we are going to just be creating surface planes for a simple metal and simple FCC metal, and for that, there is actually a very specific set of instructions that we are going to go through on how you can actually create, say, simple 100, 110, and 111 surfaces for that simple cubic crystal structure. Okay, so whenever you do surface calculations, there are a few considerations that you must take into account. Okay, one, what's the termination, right? I'm going to talk about this in a little bit. You need to consider whether the termination itself is polar, and whether the surface reconstruction that can occur. Okay, and all these can have potentially significant effects on the properties of the surface that you calculate. All right, let me start by talking about terminations, right? So let's look at, say, a simple crystal structure like lithium iron phosphate, right? essentially when we think about, let's say, the 010 surface of lithium iron phosphate, which is the surface that you see right across over here, okay? You can think about, well, am I going to terminate the surface right here, right at basically the edge of the crystal, or I can equivalently slice the surface at any point along this axis, right? So I can just keep slicing and slicing and slicing, and all these will create different terminations for my 010 surface of lithium iron phosphate. Now, usually all that you need to do is to consider what I call symmetrically distinct terminations. In other words, terminations that are unique in the arrangement of atoms. So in other words, there are terminations that are not related to each other by some symmetry operation. Okay. There are also rules of thumbs you can use to basically determine which are the low energy terminations. Okay. So the lower the energy of the surface, the more likely that that is basically the stable termination of your surface. Okay. So think, for example, in this lithium iron phosphate crystal structure, you can do a termination which actually cuts across these PO4 groups. Okay. You can also equivalently define, say, a termination that is somewhere around here, and this termination only cuts FeO6 octahedral, but it does not cut any of the PO4 groups. Okay. Now, quite often, just by considering this kind of which kind of bonds your terminations are your cleavage of surfaces are going to create, you can actually make a good guess as to which of these cleavages are going to result in high energy surfaces and which of these are going to result in low energy surfaces. Okay, so for instance, cutting the PO4 group is usually very energetically unfavorable. Okay, the PO bond is actually very, very strong. So any termination that cuts across these PO4 groups are typically not going to be low in energy. So you would try to look for terminations that are much less, that do not cut the PO4 groups. Okay. Now, another consideration, especially when you deal with ionic crystals, is whether your surfaces are polar, right? So let's consider, say, a simple sodium chloride type crystal structure where you basically have one metal plus and one anion X minus. Okay. Now, if we think of the 100 surface of sodium chloride, this is basically what sodium chloride looks like, right? So you basically have alternating sodium and chlorine atoms, okay? And if you are trying to look at the 100 surface or the 010 surface of sodium chloride, you will find that essentially all the surfaces are neutral, right? So you have an equal number of positively charged ion with negatively charged anions. Okay, so you have one N plus with for every X minus, so these two cancel each other out. So overall, your surfaces are charge neutral, right? And these are basically what I call Tasker 1 type surfaces. Okay, and if you encounter these kind of surfaces, good for you. This is one of the easiest surfaces to consider because there's no worry about long range electrostatics, because overall every single layer of your crystal is going to be charge neutral, right? Now, there are what I call the type 2 crystal structures. So here we show an example of, say, 2 plus cation with a 1 minus anion. Okay, now here, this particular crystal structure have alternating layers of X minus and M2 plus, right? So you have X minus, M2 plus, X minus, X minus, M2 plus, X minus, right? Now, these are what I call type 2 surfaces, okay? So type 2 surfaces, first of all, they are definitely not charge neutral on the surface. So quite obviously, let's say, if you look at this, you basically have a X minus at the top surface, right? And the X minus at the bottom surface. There's no compensating positive charge, right? However, the overall cell is still charge neutral and there is no polarization, right? Because you have equal numbers of, you have a symmetric distribution of charge in your slab. You have X minus at the top surface and X minus at the bottom surface, and you don't have a overall polarization, okay? So these are what are called Tasker type 2 surfaces. And also again, for this type of surfaces, you generally don't have a problem with doing your simulations, okay? Now, the third type of surface is, yep, Ayush, why don't you go ahead? What's your question? No? So if you take a look at this, you have 1 M2 plus for 2x minus, 1 M2 plus for 2x minus, 1 M2 plus for 2x minus. That's completely charge neutral, right? Yeah. Yeah. Yep. So good question. Okay. So here I'm showing a M plus with X minus. Here is actually a M2 plus. So it's a double charge cation with a single charge anion. Okay. Yeah. So it is still over. So first of all, your cells must be overall charge neutral, but you also do not want polarization. Okay. Now the Tasker type 3 surface is basically this kind of situation, right? So the classic example is the 111 surface of your sodium chloride crystal structure. If you look at the 111 surface of your sodium chloride, you will find that essentially what you have is layers of M plus and X minus, okay? And the structure is still overall charge neutral. You have 1 M plus for 1 X minus, okay? So this overall crystal structure is still charge neutral, but now you actually have a polar surface, right? You have M plus on your top surface and X minus on your bottom surface, right? So now your slab is overall, there's an overall polarization to your slab, okay? So these are what are called Tasker type 3 surfaces, right? And typically when we do surface calculations, you want to avoid Tasker type 3 surfaces because there are long-range electrostatic interactions associated with this polarization of your slab, okay? So how do we actually deal with this problem, right? The way that typically you would deal with this problem is to do what is called a Tasker type 3 to type 2 reconstruction, right? So what you would do is that you would take atoms that are at the bottom surface and some of the atoms that are at the bottom surface and you move it to the top surface. And in doing so, basically what you do is you create a overall non-polar surface for your crystal structure, okay? So this is how it works, okay? This is what is called the Tasker type 3 to Tasker type 2b reconstruction. You just move atoms from the top surface to the bottom surface or vice versa is equivalent. And essentially what you have now is basically you have a positive surface at the top and positive surface at the bottom. The overall cell is still charge neutral, and this is basically, your surfaces are of course no longer stoichiometric, but at the very least you don't have a polarization of your surface, okay? All right. Now, because your surfaces are also environment where you essentially, so surfaces actually are very different environments from your bulk, right? So you can imagine that atoms at your surface, at the surface, are actually under coordinated, right? You actually have atoms that are not you have one side where you essentially have nothing bonding to the atoms. Okay, it's not like, say, an atom in the bulk where you basically have bonds on all sides, right? And that lack of bonding actually can result in what are called surface reconstructions, okay? So first of all, there are a few different types of reconstruction of surfaces that can occur. One is, for example, just a simple surface relaxation, where essentially your atom, the interatomic distances of your surface atom to your next layer of atoms is actually different from what you actually have in the bulk. Okay, so this is a surface relaxation. You can have also what is called rumpling, where essentially you have displacement of your atoms from the original coordination. So now instead of this constant surface, you basically now have atoms that are in a zigzag manner. Okay, so there's basically a displacement of your atoms relative to each other on the surface. Okay, and you can also have what I call surface reconstruction. Yeah, in other words, a complete rearrangement of your atoms on your surface to lower its energy because of that under coordination. Okay. All right. Now, this is actually a very interesting video that I like to show. There is actually this is actually the what is called a 7x7 reconstruction of the silicon 111 surface. Okay, so diamond silicon, of course, everyone knows what diamond silicon, the structure of silicon bulk is. Okay, it turns out that the 111 surface of silicon actually has a very beautiful and complicated reconstruction that actually took about 25 years for people to basically characterize and figure out what that reconstruction is. Okay, so I'm going to click on this video, and then I'm going to share a different screen. Okay, give me a quick second. All right, let me. Okay, so this is a video showing you the 7x7 reconstruction of silicon. Okay. So this is just what you get from just directly cutting the silicon 111 surface. Okay. Okay, so hopefully that gives you a idea of how that reconstruction works. Obviously, this is a very significant, it's a very complex reconstruction. So most of the types of surfaces that you are going to try to work with, especially in this in your lab number 4, they are not going to be as nearly complex as this one. Okay, so it actually took a lot of very smart people 35 years to basically figure out what the surface of silicon 111 actually looks like. Okay, all right. All right, so now I'm going to talk a little bit about the different types of properties of surfaces that you would be exploring. So the first one is, of course, the surface energy, right? So surface energy is basically the excess energy of your slab relative to the bulk, right? Now, keep in mind that atoms in the bulk are always in its lowest energy form, right? So when you actually create a surface, you are breaking bonds, and that bond breaking actually results in higher energy. So typically, when the first thing that people always look at when they want to calculate surfaces is the surface energy, because lower energy surface generally means that they have a higher likelihood of existing in your system. Okay, so the surface energy is defined by this equation over here. You basically do the calculation of the energy of the slab, then you subtract out the energy of the bulk. Okay, so obviously the two must have the same number of atoms. So you can, for example, take the energy of a single atom multiplied by the total number of atoms in your slab, and that basically gives you this surface energy equation. Okay, and A is, of course, the surface area of your slab. So the surface energy is always defined in terms of energy per unit area of your crystal. Okay, and you have this factor of 2, right? And you must remember that whenever you create a slab, typically you always have 2 surfaces that are being created. So what you want is basically the energy of 1 surface. Okay, so this factor of 2 accounts for the fact that you have 2 surfaces. So whenever we calculate things like surface energies, one of the first things that we need to converge is basically what is the number of slab, the number of layers for the slab, and what's the vacuum size that we need to get a converged surface energy. Okay, now there are good reasons for this. Okay, if your vacuum is not big enough, basically your upper surface and lower surface can interact with each other, and then you basically don't have a converged surface energy. If your slab size is not enough, then basically the broken bonds at one surface can basically affect the bulk energy and also affect the energy at the other surface, and again your energy would not be properly converged. Okay, so you will need to converge with respect to both slab size and as well as vacuum size. Okay, so this is something you'll be doing in your lab number 4. Now there is also a consideration that very few people take into account, which sometimes can be important. So, and that is basically convergence with respect to surface area. Okay, so especially if you recall, sometimes you can have effects such as rumpling. Okay, if your surface area within the plane of your surface is not sufficient, you don't really have enough space for this kind of symmetry breaking to occur. Okay, and that can actually affect also your surface energies. Okay, now for the most part, in your lab number 4, you're not going to worry about the convergence with respect to surface area. This only occurs, this is important when you actually have symmetry breaking relaxations. Okay, so just to show you what the convergence of surface energies for copper 100 and copper 111 as a function of slab thickness, you see basically you start with 5 layers and 6 layers, 7 layers, 8 layers, and so on and so forth, and then you basically, the numbers will converge to at some high enough number, you basically have a convergence of your surface energies. Okay. Now, one practical aspect of surface calculations is the K-point grid that you will need to use. Okay. Just a note, here they did the calculations for the unreconstructed silicon 111. You will see that essentially if you don't maintain equivalent K-point grids, so remember that your K-point grid is the reciprocal of your surface size, of your lattice parameter, right? So if as you increase the lattice grid, you basically need to ensure that your K-point grid is also maintained, okay? So if you do not actually maintain the same K-point grid, basically you can get this kind of divergence behavior where essentially your energy don't converge to a fixed value, okay? So the maintaining equivalent K-point grids is basically essential so that you actually get a nice behavior like this, where you basically have a nice convergence of your surface energy to some equilibrium value, okay? Another practical aspect of surface calculations is the choice of functionals, okay? So it turns out that this is one of those instances where the PBE functional does not always outperform the LDA functional, okay? And this table shows you the different surface energies of different metals, and you are actually going to be working with aluminum 111, 100, and 110, okay? And you see that basically the experimental surface energies of aluminum is 1.14 joules per meter squared. The LDA number is about 0.91, but the PBE surface energy is actually severely underestimated, okay? Similarly, you can see this for palladium. You also see the same thing for platinum and gold as well, okay? And also titanium, right? So this is one of those instances where LDA actually somehow, because of some cancellation of errors, actually seems to perform better than your PBE functional in terms of reproducing your surface energies, okay? And this is also the reason why today LDA is still being used for surface energy calculations, all right? Now, other than your pure surface, a lot of times you'll be interested in knowing what is the binding energy of different adsorbates on your surface, okay? So this is, of course, a key consideration in catalysis, right? So when we are trying to design catalysts, let's say we want to design a catalyst for CO2 reduction, okay? We need to know what's the binding energy of your CO2 molecule on the surfaces of your catalyst, right? And people have used DFT calculations to study the binding energy, right? There's something called the Sabatius principle, which basically states that the optimal catalyst is one where the binding of your atoms, of your adsorbate on the catalyst is neither too strong nor too weak, right? So this basically leads to what is called a volcano plot, which I'm going to talk about in a little bit, right? So the way that you would calculate the binding energy is quite simple. You basically calculate, you put the gas molecule on top of your slab. You calculate the total energy with relaxation, and then you minus off the you subtract the energy of your gas molecule, and you also subtract the energy of your slab itself, and that basically gives you the binding energy of your molecule on a slab, okay? So this is actually obtained from this work by the work of Bill Goddard in Caltech, where they basically study the oxygen reduction reaction on this alloy, which is a platinum 3 nickel, okay? And they calculated the binding energy of hydrogen, oxygen, the hydroxyl anion, and the O2 gas. So all these are basically intermediates that you will be interested in if you are studying oxygen reduction on this catalyst surfaces, okay? And here are all the binding energy of this all these different species on this different sites, okay? So this is why you need to understand why this kind of calculations are so difficult to do, right? When we think about a surface, there are so many different positions where we can actually put our gas molecule, right? We can put it on top of one atom or the other. We can also put it at this bridge site, which is in between these two atoms. We can put it in this hollow site, which is in between which is this hole that is between the three atoms on the surface, okay? And all of these would result in different binding energies, okay? And of course, when we are thinking about a catalytic reaction pathway, we are typically interested in the lowest energy or the few lowest energy position absorption of the absorbates on the surface, okay? Now, so this is yet another example where they were studying basically this absorption on the copper surface, okay, and they also calculate the absorption of carbon and oxygen binding on this all these different metals, and this result in basically what is called a volcano plot, okay? So this is the binding energy of carbon, and this is the binding energy of oxygen on the y-axis, and you'll see that the best catalyst, which is the one with the highest turnover frequency, they all exist in this point. If you have stronger binding of carbon, you basically have lower turnover frequency. If you have weaker binding of carbon, you also have a lower frequency, right? So there is an optimal region for binding energies, which actually gives you the best catalytic performance, okay? So essentially here they also show that this nickel 3Fe alloy that they were developing actually has one of the best turnover frequencies for this reaction, okay? You can also do surface calculations to calculate things like what is the intercalation potential for atoms in for lithium-ion batteries. So this was actually work done by Lei Wang back in 2007, where he basically looked at the different crystal surfaces of lithium iron phosphate and basically calculate what is the voltage for extraction of lithium from each of these surfaces, right? And this actually can tell you which of these surfaces would would be the one where you basically start to extract lithium out of that lithium iron phosphate crystal, okay? This is also yet another very interesting work that is done by Wenhao San, where he basically studied the nucleation of metastable aragonite, which is a form of calcium carbonate in seawater, right? So this is something that maybe a lot of you do not know, but most of calcium carbonate actually exists in calcite. This is the typical form of calcium carbonate that you encounter in rocks and in geology. Nevertheless, there is another form of calcium carbonate called aragonite that you also frequently find in nature, right? And the strange thing is that if you calculate the bulk energy of both crystal structures, you will find that aragonite is obviously higher in energy than calcite, right? So in other words, there shouldn't be, you really should expect to find calcite much more frequently than you will find aragonite, right? And basically what this work actually did was that he did a lot of surface calculations on calcite and aragonite, and he calculated basically the kinetic phase diagram of the nucleation rate between calcite and aragonite, and he essentially shows that at certain supersaturations and magnesium to calcium ratio, you essentially have a preferential nucleation of aragonite relative to calcite, right? And this explains why you actually find aragonite in nature. Okay.
Now,
other than surfaces, surfaces are basically just interfaces between a material and the vacuum, right? Now, when we talk about interfaces, we are really talking about the interface between two pieces of bulk material. They can be homogeneous interfaces like grain boundaries, in which you basically have the same material, except that they are just not meeting at a perfect crystallographic plane. Or you basically can also have heterogeneous interfaces, okay, which you basically have one material on one side of the interface and another material on the other side of the interface, okay. Now, such grain boundaries are, of course, the special category of interfaces where you essentially have the same material. It's just that you basically have this meeting of the two pieces of crystal at some interface, right? Now, typically when we think about interfaces, we also can divide them into coherent as well as non-coherent interfaces, right? Coherent interfaces just simply means that there is some form of lattice matching between the two pieces of crystal, okay? So, and in incoherent interfaces, which are far more common, you basically just have two pieces of materials meeting, and there is no matching of the crystallographic planes whatsoever, okay? Now, for grain boundaries, we typically describe them based on the type of meeting of materials that you actually see at the interface, right? There are what I call tilt grain boundaries, where essentially you have just two crystals that are offset from each other by just a rotation, just a rotation of one crystal with respect to the other, okay? Now, there's also what is called twist grain boundary, where you basically have two crystals and then you just rotate them in this manner, okay? So, both types of grain boundaries are important, okay? And people frequently create models of such systems to basically calculate the grain boundary energy of both tilt and twist grain boundaries, okay? So what I show here is basically some examples of where interfaces, heterogeneous interfaces where which are not grain boundary related. So for example, people also study interfaces like these, where you basically have interfaces between different types of materials. Here, the top layer is basically aluminum oxide, and the bottom layer is basically your strontium titanate. And the reason why people are interested in this kind of interfaces is that sometimes there can be very interesting material properties happening at that interface, right? So in this case, what they were studying is basically what is called a two-dimensional electron gas, right? So because of the way the materials interact with one another at the interface, you basically have a gas of electrons, free electrons at the interface, and that 2D electron gas actually has very, very interesting properties, okay? People also frequently study doping and what happens to dopants both in the bulk and at the interface, okay? So this is actually work from another professor at in nanoengineering at UCSD, where they basically study liquid metal embrittlement, okay? So it turns out that if you actually have certain elements like bismuth in nickel, what happens is that bismuth have a very detrimental effect on your nickel-based alloys, right? The reason what they found was that bismuth tends to basically segregate to the grain boundaries, okay, and form this kind of bilayer structure, and that bilayer structure actually weakens the grain boundary cohesion, right? So, and that results in basically a very brittle metal that basically can just fall apart quite easily, right? And subsequently, someone actually did the density functional theory study where they basically look at essentially the cohesion of bismuth and brittle grain boundary for nickel. Okay, so this is basically some of the kind of studies that you can do using DFT. This is a much more large-scale study of the same effect. Okay, so here they are essentially looking at different solutes at iron grain boundaries. Okay, so iron, of course, is one of the most important metals that we use in all kinds of applications. Okay, and here they basically look at what happens when you actually have different types of metals at the iron grain boundaries, and basically what the segregation energy is. In other words, what elements would actually tend to segregate to the iron grain boundary, and what elements would have a lower tendency to segregate to the grain boundary. Okay, so here they basically show that niobium, for instance, have a very, very strong tendency to actually go to the grain boundary, while another element like cobalt actually doesn't have that much of a tendency to segregate to the grain boundary. Okay. This is actually work that was done by my group previously. Again, this is the same concept. We were looking at molybdenum, not iron, and we are also looking at metallic dopant segregation to the grain boundaries because, again, certain types of elements segregating to the grain boundary can actually significantly reduce the work of separation, and that actually results in embrittlement of molybdenum. Okay, so that's it for interfaces. Does anyone have any questions regarding this particular part before I move on?